coming to the final section of this network theorem. We'll discuss today Norton theorem. So according to Norton theorem, any two terminals, okay, active network consisting of linear impedances and voltage sources may be replaced by a current source in parallel with an impedance. Okay, so the current is equal to that obtained through a short circuit across the two terminals, and the impedance is that viewed across the two terminals when all the generators are replaced by their internal impedances. So the definition is already over here, the theorem rather. Now it can easily be proved. What basically we need to know is that this is the Thevenin circuit. We have just Thevenized in the previous section. We have just know how to Thevenize a given linear bilateral circuit. So this is the equivalent bilateral Thevenin circuit, which has been again converted into the Norton form as per the definition. Now this theorem, it can be easily proved by considering a Thevenin equivalent circuit. Here we have shown in this particular the Thevenin equivalent circuit. Okay, now this may be replaced, this circuit, and here in this circuit we have E naught, and we are having Z naught. Okay, ZL and IL is the current over here. There is a load current through this. Now this can be replaced by the equivalent circuit. Okay, which consists of the current source I naught. Now this has been replaced by the current circuit I naught with in parallel with an impedance Z. Okay, appearing between the terminals A and B. Now this current source here, the current source is called, okay, the current source is called the Norton's, okay, current. This current source is called the Norton's current, and Z naught is called the Norton impedance. Now the current flowing in the network, this network, is given by, how it can be written like this. Now the current flowing in the network, in this network, it will be given by IL is equal to E naught. That's very simple. IL is equal to E naught divided by Z naught plus ZL. Okay, now we will just apply the current division law, the basic law which you have already done in your +2 level. Okay, in this network, okay, to find out the value of IL prime. This is IL prime. Okay, so IL prime will be given by Z I naught divided by Z plus ZL. Okay, now if Z is equal to Z naught, okay, the load current IL can be made equal to IL. Thus from the above relation we will have I naught is equal to E naught by Z naught, which is the short circuit current of the Thevenin's equivalent network. Okay, thus we see that the interchange of voltage and current source with the help of Thevenin's and Norton's theorem, gives a method of network analysis. Okay, so our next topic is maximum power transfer theorem. So here we have just mentioned the theorem, and that is this theorem. It states that the power received by one network, okay, from another connected network is a maximum when the impedance of the receiving network is conjugate to the impedance of the connected network looking at its two terminals. So this is the basic definition, and again what we have done is that we have taken the help of the Thevenin circuit. Okay, this is the Thevenin equivalent of this circuit. Now what we do is that we'll just need a proof of that, what has been mentioned in the theorem, right? Now what we do is that we'll consider that the load impedance ZL here, okay, the load is impedance ZL, okay, is connected to an AC voltage, okay, E naught obviously, and internal impedance Z subscript G. Okay, so here we'll write Z subscript G is equal to R subscript G plus J X subscript G, and ZL equal to R subscript L plus J subscript XL, where Rg, what is Rg? Rg is the resistance, okay, and Xg, it is the reactance, okay, of Zg. Similarly, RL and XL, X subscript L rather, are the corresponding quantities of Z subscript L. So the load current phasor, is I subscript L is equal to P subscript G by Z subscript G plus Z subscript L, which is again is equal to, in fact here we have considered not V subscript, should be E naught in the place of this. We'll write E naught, again so we'll write E naught, okay, divided by R subscript G plus R subscript L, okay, plus J X subscript G plus X subscript L. So now the power delivered to the load is given by P is equal to IL square into RL, which is equal to E naught mod of E naught square RL by Rg plus RL whole square plus Xg plus X subscript L whole square. So this is the power delivered to the load. Okay, now what we need to know is that here Rg, R subscript G and X subscript G are fixed. This one is fixed, whereas RL and XL can be varied. This can be varied. Okay, so P is maximum, that is power, if XL is varied, that is when XL is equal to minus of Xg. So this is the condition of the series resonance. Under this condition, the above equation may be written as P is equal to E naught mod of E naught square RL, okay, by Rg plus RL whole square. So P is maximum, maximized rather. P is maximized by varying RL. So under the maximum power condition, dP by dR subscript L must be equal to 0. Okay, which gives RL equal to Rg. Thus, for maximizing power transfer to the load, we have maximum power transfer to the load. We have ZL is equal to RL plus JXL, and which is equal to Rg minus JXG, okay, which is Z asterisk G, where Z asterisk G is the complex conjugate, of the source impedance, Z subscript G. This establishes the maximum transfer theorem. This establishes the maximum power transfer theorem. So the maximum power delivered to the load is given by this much, that is P max is equal to E naught square modulated by 4 Rg. Okay, so this is what you'll get. Okay, so with this we'll just finish up this portion of the network theorem. Next we'll deal with the AC circuit. So until then, thank you.